So hello again. Tonight we're going to talk about cooling by applying energy. So it seems counterintuitive that when something is hotter, it has more energy of motion of atoms and molecules, and that this motion translates into infrared energy, which we think of as heat and we measure as temperature. So why would applying energy reduce something's temperature? The straightforward answer is by decreasing the motion of atoms and molecules, the amount of infrared being produced, the amount of heat being produced is reduced. Therefore, the measurable temperature of the object is reduced. But you have to have a very precise and specific application of what kind of energy, the wavelength, the pulse duration, the angles, all that kinds of stuff. And it's based upon one of my favorite physics principles, which is radiation reflection pressure, as established by Nichols and Hull in the early 1900s. And then later proven by Bell and Green in the 1920s, 30s. But in 1997, there was actually a Nobel Prize in Physics awarded for what they referred to as laser trapping and cooling. And what they did was they used magnetic fields to start corralling things together, and then they used the lasers from different angles to push on the atoms back then to reduce their motion, and by reducing their motion, it reduced their infrared output and therefore the measured heat. So once you've done all of the other stuff to get things down to low Kelvin measurements and temperature, then you use your laser trapping and cooling to bring it down even more. So you start with electromagnetic coils, and you use that to corral or confine. So you're taking something that's atoms, like rubidium atoms, that are cooled, and they're still moving about a bit, and use a magnetic field to push on them, so it kind of like confines them and makes them stop moving at a very large scale, but they're still moving at a very, very small scale. So you then use lasers in infrared. I mean, it shows red here, but they were infrared. Lasers from different directions to kind of push on the atoms to tamp them down further. And if you're into the physics of it, here's the physics of it. It's often referred to as Doppler cooling. And remember, the Doppler shift is something that we measure as if something's moving away, you get a red shift. If something's moving towards you, you get a blue shift. If something's sitting still at a fixed distance, there's no red or blue shifting. And it looks like if something's not moving, then the photons that you apply to it don't affect the atom because it's stable. It doesn't pick up, it doesn't release, it just stays there. So the energy you're applying doesn't have a net effect. But if the atom is moving away from you, now moving away or towards are real-time instantaneous assessments. Like if it's vibrating, that means it's got a sinusoidal process, and it's swinging this way and that way and this way and that way and this way and that way. And if all you do is you tamp on it whenever it comes at you and you keep hitting it, then it will reduce the amplitude of that sinusoidal, the sine wave. And if you have something coming from the other direction that's also doing the same thing, you're reducing the movement of those atoms and therefore the amount of infrared heat it could produce. So moving away doesn't absorb anything. Moving towards, and it starts to absorb something. And when it absorbs it, it kind of recoils from it, gives off a photon, and now it's more stabilized. Its velocity has changed. So the idea is, if you can think of it as a bouncing ball between two plates, and as the bouncing ball starts out and you move the plates closer and closer together really quickly, the ball goes and then comes to a stop between the plates. That's all they're doing. Or here's another simple analogy: Whac-A-Mole. You go to a game center, amusement center, and they have this thing called a Whac-A-Mole. It's actually a intellectual property, copyrighted, trademarked thing. But it's a game, and you start the game, and these little mole heads pop up out of the holes, and then you have a mallet, a rubber mallet, and you whack the moles. So think of it as the atoms or molecules come towards you, you take your energy and you use radiation reflection pressure to transfer momentum via the photons to the mole, and it pushes it back down. Now, you don't have to push it down so hard that it'll drive it out the bottom of the game. You just have to push it down hard enough and fast enough so that you catch it on its way up and you push it back down, and it's not going to come up again for a time. So that's an analogy of it. But is this real world stuff? Is this proven science? Well, here's an example of how proven it is. There is a thing called the Laser Cooling Lab, and it is currently aboard the International Space Station. And what it does is it takes rubidium atoms as a gas, and then it cryogenically cools it, and then it will use laser beams from different directions along with a magnetic field to squeeze the rubidium atoms to reduce their energy. And by the time the lasers have done this, then it gets to 10 nanokelvin, or 1/10,000,000th of 1 Kelvin. Absolutely.
I have a question.
Yes.
Cryogenics is getting used a lot lately,
Yep.
and I'm not exactly sure what it means, like in this context.
When you cryogenically cool something, you're looking to change the state of matter of that material. If you freeze something, freeze is a more common term, and it just means, well, if I freeze that, it's going to go from liquid to a solid. Okay. If you cryogenically cool something, you're going to take it from a solid back to a liquid.
Solid.
Very, very cold liquid. So when you go to launch your rocket and you have oxidizer, and the oxidizer is oxygen, to get more oxygen to fit in the tank, you make the oxygen really cold, and the molecules get close together, and you can fit more oxygen in the same size tank. And then as you release the oxygen, you get a very large pressure change, and it goes from a liquid back to a gas. So cryogenics is literally just reducing the temperature of something until it changes state.
And you might do that because you need the space. I mean,
yeah, generally it's because you need the space.
So cryogenics is usually just applying to gas, and that you're getting that to be cooled into a liquid. Okay, I got it. Thank you.
Yes. Now, under pressure, as well as cryogenically cooled to a liquid, you can actually make certain gases behave like metals. So at the core of Jupiter and Saturn, you have a great deal of hydrogen that is under massive pressure and cryogenically cooled out in deep space. And so the hydrogen starts to go from just a liquid to a very, very dense liquid and starts behaving electromagnetically like a metal. And when you look on the periodic table of elements, yes, essentially hydrogen is a metal.
They did use cryogenically a lot with people being, dying and trying to preserve them.
Yes,
so,
but that's nowhere near 0 Kelvin.
And it's nothing like, they're not being cooled because they're a gas.
No, they're being cooled because the presumption is that will shut down decay processes. It will shut down the chemical compounds that degrade tissues and such. And therefore, once they figure out how to thaw you out without you falling apart, they can bring you back. And to date, lots of people's whole bodies and even just heads have been frozen, and nobody's ever been brought back. However,
yeah, they're frozen. They're not. I wonder why they use a cryogenical word there, because
The
it's really
temperature, the
what
temperature, it's well below freezing.
you can put somebody's head below freezing,
Yes,
and
but
it's not
there's no guarantee that when you thaw them out, however you do that, that they're still going to be in good enough shape to reactivate their head.
But didn't it sound just better to say cryogenic rather than to say we're going to freeze your head?
Well, it is a more accurate term because we're not just taking your head down to like 0 degrees Fahrenheit. We're taking you down to maybe 100 degrees below 0 Fahrenheit. The fun physics aspect of cooling something down so low to near 0 Kelvin is that you create what is known as a Bose-Einstein condensate, or a BEC. Bose was one guy, Einstein was the other. Together they came up in the early 1900s with this concept of what if we reduce the amount of energy of motion in atoms? What would be the physics behaviors of that? And they said, well, conductivity will improve, so superconductivity. A lot of the things that we consider as chemical processes would cease to function because they can't transfer the materials they would otherwise do so. So they can't transfer charges. So if you have a gas of rubidium atoms and you cryogenically cool it to a liquid, and then you bring that liquid very close to 0 Kelvin, the liquid will essentially have a surface tension of the liquid that goes throughout the liquid. So the liquid sitting in a specialized glass container will lose its electrical affiliation with the glass molecules of the container. So if you started pouring the Bose-Einstein condensate out of the container and then you righted the container, the material, the molecules, the rubidium atom will continue to pull themselves out of the container against gravity, and the entire container will be empty. Sort of it kind of exhibits polymer characteristics. And they've seen this happen. It's reproducible. But when you turn off the trap that's keeping it cold, within a fraction of a second, it loses the effect. It loses the Bose-Einstein condensate state of matter. They've realized that the reason why it so quickly returns from near 0 Kelvin and loses its Bose-Einstein condensate properties is because of gravity. Gravity exhibits an attraction to the rubidium atoms and pulls them down. And if you have something pulling them down, that is a velocity in a direction and therefore an energy. And therefore, once you turn off the cooling, it doesn't stay cool, even if it's in a vacuum chamber, because gravity is still trying to pull the atoms down and it makes them oscillate. So they're saying that by having the laser cooling lab on board the International Space Station in microgravity, we'll lose most of that gravitational attraction. And we might get to see that if we turn off the trap, the BEC effect might last 5 to 10 seconds, which is still not a long time, but it's, going from tiny fractions of a second to multiples of seconds is kind of the thing that, quantum computers are all about. The quantum computer can be reliable and accurate for, milliseconds. And when they made it to, we breached the second barrier. So it went from milliseconds to a second, and that was earth shattering. And now we're talking about a similar concept in Bose-Einstein condensates, that we can get them in the absence of gravity to last not just fractions of a second, but maybe 5 to 10 seconds. So the concepts of physics progress, but you have to create the technology to make it happen. But there may be other things that once you remove gravity, that you'll see that you won't see on Earth. So it's good to have this in a microgravity environment. Now, why is it not much longer than 10 seconds? Because remember, it's a microgravity environment. So even though you see everybody floating around inside the ISS, it's not because there's zero gravity. It's because the space station is falling back towards the Earth at the same rate that they're moving inside the space station. So the space station is falling out from underneath them, kind of like a roller coaster ride that lasts for a long period of time. So I did some research, and I got the parameters for when they were doing their Bose-Einstein condensates. They were cooling atoms, not collections of atoms, individual atoms, not molecules or chemical compounds or materials, just bunches of atoms. And the diameter, the size of the area that they were holding the atoms in, was 100 micrometers. That's 100 millionths of a meter. Very, very tiny amount of stuff they were holding in there. Because the first thing they had to do was compress the atoms, the magnetic field was 90 Gauss. That's a very strong magnet. The diameter of the laser beams coming in from all the angles, each laser beam was 3/4 of a millimeter in diameter. So the trap was small, the beam was massive compared to the size of the trap. So 0.75 millimeters is huge compared to 100 micrometers. So the beam was much larger than the collection of atoms that they were trying to deal with. The particular wavelength of the lasers was 785 nanometers, which is near infrared. No, it's actually near infrared band. It's actually into infrared. How often they would cycle the laser beam off and on was 10,000 times a second. So the beam isn't just turned on, the beam is like smacking the atoms, trying to corral them even further. The maximum amount of displacement they got to move the individual atoms was 400 micrometers, which means the total effect they were having was to squeeze the atoms by 400 millionths of a meter. So small space, huge magnetic field, very small beams, but bigger than the target, infrared, and they weren't moving it all that much. Then they scaled it up. Now this takes into account a new thing that they rationalized that if we can synchronize the laser beams on each side of the material so that they're hitting at exactly the same time, but they're out of phase with one another, then it's like having two plates and you've got a vibrating ball between them, and you smack the plates from both sides at precisely the same time with the same level of energy, and the ball that's bouncing around will very rapidly just zip, but you can do so with a much bigger target than an individual atom. And this is actually called not Doppler cooling, but Sysyphus cooling. And that's just, ancient mythological Sysyphus. So Sysyphus cooling. And what they're doing is they're taking the laser beams and on opposite side, putting one out of phase with the other, and they're firing them very precisely at the same time to hit the material from both sides. And they found they can actually apply more force to it doing this. So now instead of just cooling individual atoms, they can actually cool compounds. There is documented, confirmed evidence of what they call magneto-optical trapping. So the magnetic field starts to squish things down, and then these specially modified lasers smacking from all sides in unison. You can actually take strontium fluoride, as a compound and reduce its temperature. You can take calcium fluoride. You can take yttrium oxide, calcium hydride. They've tried a number of different compounds, and the compounds have to have some ability to be initially corralled by a magnetic field. But they're not shooting for 0 Kelvin. They're not shooting for a Bose-Einstein condensate. They're just saying, we want to scale it up and see what kinds of, not atoms, but molecules. How big a thing can we dramatically reduce the temperature of it? But instead of getting down to, billionths of a Kelvin, they're only getting down to 25 thousandths of a Kelvin, which is still super cold, but they're not looking for, absolute zero coldness. They're just looking for, if we can reduce the motion of the molecules inside of compounds, we can refrigerate compounds much more cheaply and efficiently with less energy than we can with mechanical processes, because there's a lot of industrial processes that these compounds are based upon. They require a lot of mechanical equipment to refrigerate down to these cold levels. So they're getting to lower temperatures with essentially no moving parts. Goodness for industrial processes. But as they move up from individual atoms to molecules of specific compounds, they're finding that it's actually getting easier. Your lasers have to be more precise, but the whole instrumentation is easier. That 90 Gauss magnetic field now only needs to be 0.6 Gauss. So a lot less magnetism needed to move heavier things. It's because the heavier things have an inherent stability already. So you don't have to, they're not flying around wildly and you have to corral them. They're just moving about a bit. So you have to push them a little bit. They shortened the wavelength from 785 nanometers, which is in the near infrared band, to 663 nanometers, which is deep red. So the laser would be up in the dark red visible spectral range. That increases the amount of energy each photon carries to each particle of the material. So hitting it harder. They changed the beam pulse frequency from 10 kilohertz to 5 megahertz. That's thousands of times a second to millions of times a second. So there's more energy per smack, but we have to smack it more often. And they also changed the duration of each smack down to 275 microseconds. So when the photons come out there and smack the material, they smack the material for a very brief amount of time. And they measured the amount of spectral density, the amount of photon power per square centimeter and over megahertz. That's actually a measurable value is milliwatts per centimeter squared per megahertz. Turns out to be 5, which is a relatively low number. Something that even LEDs can get into. And you remember they could only move individual rubidium atoms 400 millionths of a meter. Well, they can actually move molecules of calcium fluoride 240 thousandths of a meter per second. So there's a lot more persuasion of the materials as they start getting higher. So they can cool to a lesser degree, not colder, but they can still get it cold, still get it cryogenic, and it takes actually less effort to do it. It's just a very specific application of the photons. This is the one I didn't know about. You probably have heard of laser hair removal or laser tattoo removal, or if somebody has a lot of dark spots on their skin, laser pigmentation removal. Well, the laser that they use for that has a fair amount of energy in it. they need to deliver deep infrared, 1,064 nanometers, up to 100 milliseconds to either destroy a hair follicle or destroy the pigmentation of a tattoo or to get rid of a dark spot on the skin. But that also leaves a lot of heat in the skin. They found that by adjusting the wavelength of the laser, they could actually heat up the spot, destroy the hair follicle or the pigment particle of the tattoo or the pigment in the skin, and then immediately switch over to the laser cooling and cool the skin down where you don't feel it as much and there's less damage to the adjacent tissue. So laser skin cooling is a thing that's actually used in laser hair removal. And it has a fancy term. It's called laser-induced selective photothermolysis of hair follicles in human skin. And there's actually a National Institutes of Health research paper documenting the proof of it. So I was like, that one was something I didn't know going to this. Laser hair removal uses laser skin cooling. They're using a laser to cool skin? That's counterintuitive. So what if we take it from atoms to molecules of compounds to areas of skin, and we say, well, can we extrapolate this out further and let's say cool a small sheet of aluminum? Well, aluminum is a metal. It's got molecules that are moving around. Could we tamp those down and cool the aluminum panel? I don't see why not. Physics doesn't constrain itself to saying, no, you can't do it, but you're going to have to change some things. Well, if you notice, we went from 90 Gauss to 0.6 Gauss to 0 Gauss because there's no heavy magnetic fields on laser skin cooling. So as we come up that curve, we ditch the magnetic field because we don't need to corral the materials. I mean, it's a sheet of aluminum. The atoms are not popping out of the aluminum. They're still held in the aluminum. But we're likely to have to change the beam pattern and the frequency and maybe what wavelength we're using. And so points on the curve, we adjust things appropriately. Now, why would that be something meaningful? How about it creates a residential air conditioning technology with 0 moving parts? No compressor, no condenser, no fan for the condenser, no circulation pumps, no refrigerant fluids under various pressures, no valves, no big capacitors for high motor start currents. And instead of running at 220 volts at 50 amps, it could probably easily run at 120 volts at less than 15 amps. Because all you're doing is you're cooling off a sheet of aluminum. Now, you're not trying to make it cryogenically cool. You just need to bring it down where, like a normal air conditioning. If you can get it to at least 10 degrees below ambient, that's cold enough. So if you could get this sheet of aluminum sitting inside of an air duct and the air coming in is 80 degrees, if you can get the aluminum to reduce the air temperature by 10 degrees, more than enough. If you can
so they produce that today? They do that for residential air conditioners today?
No, they don't. In fact, I talked to one of the air conditioning guys that I've used their service since the 1970s when I bought this house. And he one time said, yes, there is technology for solid state air conditioning. But once I put it in, you'd never see me again because the only moving part is a fan.
So they don't have any fluid going through it?
No.
So you wouldn't get the algae buildup?
Correct.
Wow, I want that.
Now the technology for cooling air by a solid state has existed for some time, and it's practically usable in northern climates where the temperature gets so low that the whole, Bernoulli air compressor, refrigeration fluids, that stuff goes out the window because you can't transfer the heat effectively enough. So you need another mechanism. And for that, you can look up Peltier cooling. That's a particular compound of bismuth. They make little tiny pillars of it, and they put that between two metal plates, and you run a DC current through the bismuth little pillars, and it transfers all of the electrons of heat from one side to another. And then you blow air over the side that gets hotter. So it takes an ambient and transfers the ambient from one side of the cooling chip to the other. And then you remove the heat using a fan from there. But this side of it, you put fins on it, and that's where you let the air duct inside your house blow air over it. So it picks up heat, transfers the heat to the back, and then the fan blows it away. So no compressors. The only moving part is the fan. But this is actually even better because it'll be more effective and you can make it larger for less money. If you stop and think about it, an air conditioner, when you adjust the thermostat, does not adjust the effort of the air conditioning unit. It just adjusts how often it's going to turn on and turn off. Once it turns on, there is no like, well, just do it a little or do it a lot. There is, it always does it a lot. And the a lot is based upon the design specification of the compressor. So if somebody says, how big is your air conditioning unit? I've got a 3-ton unit. Well, they're talking about how much force can be used to compress the gas and then allow it to expand. And when it expands, it takes the heat with it. Well, in this particular case, it's, well, you can adjust the electrical current or the duration of the pulses, and you can actually change the effect it's having without switching it off and on. So it's more like a heating unit. If you remember old style cowl rod heating units where it was a coil of metal and you'd put current through it, and if you adjust the amount of current you're putting through it, you can change the amount of heat it's producing. Air conditioning doesn't work that way. It's either on or off, which is always amazed me when somebody will get in the car with me and they go, I want it to be really cold, and they'll set it down to 60. Like, you know, the air is not going to get any colder coming out of the duct. It's just going to be on more often. Air conditioning. So it all comes down to computer control, specific application, precision is the key. So you can set a thermostat to say, I want the ambient temperature coming out of my air conditioning ducts to be 70 degrees. And you can measure that. Well, you can take the 70 and then compare that against the ambient going into the air duct, which might be 80, and say, okay, I'm taking in 80. How much energy, how much density of photons per second do I apply to that aluminum sheet in order to get the output temperature to be 70 degrees? And you can ramp it up slowly and then drop it down slowly. So it's not this shuddering off, on, like an air conditioning unit. But why use lasers? Well, when they were first doing this and coming up with the physics principles, lasers were the most effective, coherent light source they had available to them. So, you know, in a laser, each photon has the same energy, the same wavelength, the same frequency. When the laser switches on and the photons bounce back and forth inside the containment, and then eventually they go out through the mirrored surface that's less mirrored, all the photons exit in the same direction. And they exit at roughly the same time. So they're in phase and collinear. But for what we want, you don't need the collinear. You can use lenses to adjust the beam, and you absolutely don't need them to be coherent in phase. So the one thing you can't change is the wavelength dynamically. It is whatever the emitter is. So all you really need is a lot of photons and very precise control over their emissions. Hey, LEDs have advanced considerably, as I was showing you earlier. LEDs have advanced considerably, and we can use computers to control them being turned off and on. And if you have an LED and you change the pulse width of how often you're turning it on, and you change how often you're turning it off and on, you can adjust the brightness of it without any mechanical dimmer, just done in software.
Well, it just looks like you're changing the brightness.
Exactly, because our eyes can't perceive that flicker. But if you ever have a video where somebody's taking a video of an LED, and why is the LED blinking? The LED is always blinking to reduce the amount of power that the LED is consuming and to reduce the amount of waste heat the LED is producing. Even automobiles, if you look at videos of electric vehicles and the guy's got his headlights on, the headlights are going, because you look at the headlights and you think, oh, they're so bright, they're always on. No, they're not. They're being flashed at you very, very, very fast, probably more than 200 times a second, just to reduce the amount of power that the headlights require. So put the computer control behind the emissions of photons of a variety of different LEDs at different wavelengths and see what works best. So in conclusion, quantum cooling, which I like to call it quantum cooling because somebody already stole electric cooling and electronic cooling for that Peltier stuff. And this is more like, well, we're stopping the motion of things at a subatomic or nearly subatomic scale. So we'll call it quantum cooling. Yeah, it seems plausible to more than just atoms or molecules of elements to larger materials. And if we can cool a sheet of aluminum very thin at 10 inches by 10 inches, we can create electronic or quantum air conditioning. And if we can drop it just 10 degrees, we don't have to get to 0 Kelvin anywhere near that. But, if we could make it 20 degrees, that would be even better. It would kick the pants out of the normal HVAC systems. But even 10 degrees would certainly be competitive with it because it's a lot less expensive, fewer moving parts, higher reliability, lower cost. Think of it as internal combustion engines versus electric vehicles. Electric vehicles have fewer moving parts, so they're going to be more reliable. Quantum cooling, fewer moving parts, should cost less and be more reliable. But since it's bleeding edge new technology, I'm sure that somebody will collect the appropriate profit margin and it won't come out initially being anywhere near as cheap as it ultimately will be. But you can remove one more part. Have you ever seen those fans that don't have any moving parts? I'm not talking about the fans that have the fan in the bottom. I'm talking about the fans that just have rods and they conduct electrostatic charge through the rods and it ionizes and moves the air molecules. It was Dyson's original fan, the one that Sharper Image had. And there was only one downside. When you ionize air, it produces ozone, and a high concentration of ozone is not good. So once you move the air, it's ionized air, you have to have a reverse current set of rods to discharge the ozone to convert it back to safe air. So if you want to get rid of the fan that's moving the air inside your AC unit, then electrostatic discharge of the air, and then you reverse the discharge to get rid of the ozone. So if they can do this on an even larger scale, maybe we cool the surface temperature of the carbon dioxide above the oceans and therefore cool the oceans. Or maybe we go for the ultimate prize and just use this technique to cool the oceans themselves. But as we were discussing when we were talking about weather modification, beware that you could take this to the dark side. So if you could make the cooling not just 10 degrees, but 100 degrees different from the ambient, you could become an adversary to the dark night. You could become Mr. Freeze. And as usual, lots of links. I even included a link on Mr. Freeze for people who didn't know who he was. Okay. Comments?
Very interesting topic.
Yeah, I had heard about, the Nobel Prize for laser trapping, and it was, used to bring things down into the Bose-Einstein condensate level at small fractions of a Kelvin. And you don't actually say degrees Kelvin because that's kind of redundant. You say degrees Fahrenheit and degrees centigrade, but Kelvin, you just say Kelvin because it's a measure of energy. It's not a measure of temperature or energy of motion. When I started looking into this, I had heard that they were starting to use it to cool molecules, not just individual atoms or collections of atoms, but compounds. And I said, there's an industrial reason for that. And then when I found out the list of chemical compounds that they were cryogenically cooling, oh, I understand. Those are chemicals they use on a regular basis in industrial processes. And if they can get rid of the mechanical big machines they use for cooling and make them very much smaller, there's a lot of money on the table there. A lot of reliability, less maintenance, less energy costs. And remember, if they can make the cooler to operate from electricity without any fossil fuels, they can throw in some solar panels or wind turbines and they don't have to pay the bill for the fossil fuel. So not only is the equipment cheaper and more reliable, the fuel source is free.
It's going to knock a lot of people out of work, though. There's going to be backlash.
Yeah, but when they got rid of the horses and they brought in the horseless carriages, nobody seemed to care about that because they were solving a problem.
Yeah.
They were getting rid of all the horse manure. Well, if you look at all the pollution resulting from the burning of fossil fuels, that's a lot of manure in the atmosphere. That's affecting the planet. So if we can find a way to do this, next generation won't have to learn HVAC. Next generation will have to learn quantum cooling. Current generation, if they're towards the end of their career, maybe you give them an incentive at the federal level to retire early. Maybe you give them a federal incentive to retrain to understand quantum cooling. Because remember, the AC guy that worked on the HVAC at my house knew all about electronic cooling. He knew it as his competition. So he understood it. He studied it. He understood all the ins and outs of it. So it's not like he was in a vacuum and this new technology was just going to take his job. He was already preparing for it. I think there's a portion of the workforce that will do the same thing as technologies change. That, yes, a lot of people would just kind of sit on their thumbs and not re-educate themselves or not have a desire to re-educate because, my job in the fossil fuel industry, it'll always be there. Well, you know what? When I was in my first year of college out at Broward Community College, and I was taking data processing, I said, even if I can't get a career writing software, I'll always have a job as a key punch operator.
Definitely.
Hey, punch cards are gone. Punch paper tape is gone. Magnetic reels of tape are gone. Like all the stuff that would be my fall back on where I wouldn't have to learn anything more than I ever learned in college. All gone. I'm having learned stuff. Gee, I'm learning new stuff pretty much every week nowadays. Like laser skin cooling. Didn't know that last week. Any comments or questions before I stop recording?